Modeling risk factor interaction using Copula functions. Introduction. Modern financial instruments are basically characterized as nonlinear, non-stationary processes functioning in complex conditions of multiple stochastic disturbances. Such conditions require development and application of non-traditional mathematical models for adequately describing the processes necessary for solving the task of forecasting, risk estimation, and decision-making. This is especially true to financial risk analysis in the case of multivariate problem statement. Simultaneous influence of risk factors and their interaction may result in much higher losses than available simplified models indicate. They do not take into account possible interactions. That is why modeling of risks in the problems of risk management, especially in case of large-scale system, should not be limited to analysis of separate factors. Such models should also take into consideration possible interactions between the risk factors. Statement of the problem. The purpose of the study includes solving the following tasks: constructing multivariate statistical models with known mutually dependent principal factors on the basis of copulas and distribution functions, studying the possibilities of application of the methods related to random matrices theory to analysis of the dependency measures, analyzing the possibility of application in eigenvalue distribution of correlation matrices related to different dependency measures and distribution of distances between the eigenvalues with the final purpose of determining the number of principal factors in a model. Estimation of risk dependencies. The proper probabilistic description of a system, including a set of stochastic processes, is the following probability: P of x1 is less or equal than x1, xn is less or equal than xn. That is, the joint probability distribution x1 to xn. The distribution contains information related to the process's dependency structure and marginal distribution of each random variable. To distinguish between description of dependency between these random variables, the special linked functions can be used, known as copulas. Definition 1. The function c from 0 to 1 n to 0 to 1 is called n copula if the following conditions are held: c of f1 to fn equals 0 if there exists j such as fj equals to 0, c of 1 to 1 fi 1 to 1 equals fi. C is an increasing function. Thus, copula is sufficiently completely defining the dependency structure between the random variables selected. However, the direct practical applications of copulas to description of tens or hundreds random variables meets definite difficulties. First, selection of appropriate copula family suitable for determining the copula forming the dependency structure by some parameter estimation is rather difficult. When the dimensionality is high, the number of copula parameters is growing substantially, and the problem of parameter estimation arises due to incomplete observation. For example, maximum likelihood procedure for parameter estimation may not work. If risk measures are estimated for high-dimensional copulas, the Monte Carlo procedures cannot be effective. To solve the high-dimension dependency modeling problem, it is proposed to detect principal factors in the manner as it is being done in the economic and financial model building procedures. Then the influence factors can be modeled via copulas and marginal distribution and appropriate dependency measures. Though here the problem comes to being of determining the number of principal variables for which the joint distribution is constructed. There are several specific features that are desirable for a dependency measure to possess. 1. It should be defined for any pair of continuous or discrete random variables x and y. 2. The measure should be symmetric. 3. It should be equal to 0 in case of independent random variables. 4. It should be limited to the range of -1 to 1 and reach the lowest and highest values when both random variables are, respectively, counter-monotonic and equally monotonic. 5. It can be expressed via the Pearson linear correlation coefficient in the case of two-dimensional normal distribution. 6. It distinguishes not only between random variables, but also provides a measure of distance between them. 7. It should be invariant, relatively continuous, strictly increasing transforms. 8. If a measure exhibits all the features mentioned above, it is called the dependence matrix or measure. Expanded multivariate model. To create a model for multivariate financial system functioning under influence of external factors and dependent on them financial instruments, we hired a model on the basis of combined marginal distributions and copulas for the basic observable variables. As dependent variables, the financial derivatives were used. It should be noted that the model is not limited by the independency requirement for the basic factors. The joint distribution can be written in the form h of x1 to xn, where f1 to fn are marginal distribution function for separate risk, c is n copula that characterizes the dependency structure between the risks. Consider as an example Archimedean copula that can be presented in the form c of u1 to un. The universal copula generating algorithm is based upon the following representation: c of u1 to un, where c2 is a copula for the first k components, c1 u1 equals to u1. To generate the data from the joint distribution, the following steps should be performed. Generate n independent random values nu1 to nu-n, then sequentially compute the following values: u1 equals to nu1, u2 equals to c2 nu2 u1, un equals to cn nu-n u1 to un minus 1. The derivative financial instruments. To derive financial instruments are related the contracts, the cost of which depends on some other financial instrument, stock index, or actual interest rate. To study the possibility of modeling the financial system with such derivatives as options, forwards, and futures in conditions of large data bases, the model should be expanded with actual computed costs according to the methodologies used in practice. In practice, for analytical description of currency options, Germin-Colhagen formula is often used. That is a special case of the Black-Scholes expression for determining an option price. The Germin-Colhagen model is based upon the three basic restrictions: absence of tax or restrictions for market operations, invariability of riskless interest rates within the period of a contract, actual exchange rates for currencies except random values having log normal distribution with constant standard deviation of sigma. The forward contract is a standard document that provides obligations of a person to purchase or sell stocks, good or currency at some predetermined moment of time in the future, and on predetermined conditions with the price fixed at the moment of signing the contract. The cost of a forward contract for a selected currency is calculated according to the following formula: V of t is equal to xe to the power of minus rft minus k e to the power of rdt. Here x, k, rf, rdt are the same parameters that were used for calculating an option cost. The futures contract is a standard document that provides an obligation to purchase or sell stocks, goods or currency at the predetermined moment of time and on predetermined conditions in the future with fixed price at the moment of fulfilling the obligations by the contract sides. The futures of euro-dollar type are the futures contracts with average interest rate according to the interbank rates, LIBOR, London Interbank Offered Rate. There also exist the futures contracts for other currency pairs. The euro-yen futures are nominated in Japanese yen The Euro-Swiss are nominated in Swiss francs, etc. These contracts are based upon 3 months interest rate and are distinguished by the terms of their actions from several months to tens of years. The contract cost is computed via the following formula. Vt equals 10,000 times 100 minus 1.25 Ft, where Ft is interest rate. The coefficient 0.25 is related to the 3-month contract. To model the systems with the futures contracts of euro-dollar type, the model should take into account the dependency structure for the currency rates and the LIBOR interest rate at a separate random value. The traditional futures contracts have a cost formula similar to the forward contracts, and the use of formula provides a model with the same features that are characteristic for the forward contracts only. Computational experiment. As statistical data, the following daily exchange rates were taken: US dollar, English pound, Swiss franc, and Japanese yen with respect to euro for the period from 2000 to 2007. The joint exchange rates distribution model was constructed on the basis of Copula. To develop experimentally multivariate model, the futures and options were used as derivatives with linear and nonlinear costs with respect to the basic financial instruments. In the formula for cost, the following riskless values of interest rates proposed by central banks were used: Japanese yen of 0.5%, Swiss francs of 2.75%, English pound of 5%, according to Bank of England bank rate, US dollar of 3.25%, according to Federal Funds rate, Euro of 3%, according to Eurozone refinancing rate. The image is depicting the matrix of Kendall-Rank correlation coefficients for the noiseless model. For example, the matrix of linear correlations contained lambda max equals 8.8475. Generally, the 4 maximum eigenvalues were as follows: 318.7, 69.6, 16.6, and 12.5, and all other 480 eigenvalues exhibited positive values less than 1.02. For the empirical correlation matrices was compounded empirical distribution of distances between the eigenvalues transformed via Gaussian expansion and theoretical distribution of distances for the corresponding symmetric random matrix in 5. The empirical distributions for correlation matrix and theoretical distributions for the random matrices turned out to be the same for the main bulk of eigenvalues except for the largest eigenvalue of empirical correlation matrix. This eigenvalue was much larger in comparison to theoretical distribution. For the linear correlations, it was equal to the level of 99.9992%. In the right tail of the distribution, 5% of eigenvalues exceeded theoretical threshold of 95% of observations, and theoretical threshold of 97% exceeded 2.7% of the eigenvalues. The image is depicting the matrix of Kendall-Rank correlation coefficients for the model with noise. Empirical density of distribution for distances between the eigenvalues of empirical matrix of linear Pearson coefficients and theoretical density of distributions for distances. As a result of performing the computational experiments, it was established the following. The distributions of eigenvalues and distances between the eigenvalues for empirical correlation matrices with the use of different dependence measures demonstrated quite similar behavior. The computed distributions of the eigenvalues provide a possibility for further correct determining the principal factors for constructing adequate models for the processes under consideration and risk estimation. Conclusion. As a result of the studies performed, it was established that the spectra of relatively small eigenvalues for the linear correlation coefficients ρ, rank correlation Kendall coefficients tau, and the rank correlation Spearman coefficients ρs in the case of adding some noise are particularly similar to the theoretical spectra of random matrices. That is why the optimal Markowitz portfolio that corresponds to small eigenvalues should be compiled only after filtering of statistical data. In our opinion, it would be logical to concentrate in the future research on refining the results achieved for computing theoretical distribution of the eigenvalues and the distances between them for symmetric positively defined matrices, the elements of which are restricted within the interval of -1 to 1. The problem to be solved is also touching upon investigation of influence of nonlinear, strictly increasing transforms on the distribution of empirical dependency measures matrix eigenvalues. And it would also be interesting to study the dependency measure in form of Matsushita-Hellinger matrix, as well as compile other possible measures. Thanks for your attention.